So in this dashboard, I'm comparing the values of 31 sigmas, 15 to the left of sigma 0.5, 15 to the right or a higher values, and all it is incremented by 0.005. And so I also have a graph with the y sign and the x cosine, and it also has a flexible center line so that we know in what quadrant all these plotted sigma values. So what is returned is the location of the sigma values. So what you see there is the sigma value occupying that space. And also the fact that the center line is erased and then recreated for each loop. We now have a clear idea of the quadrants, how many quadrants are used sometimes there could only be one, sometimes two, sometimes all four. So we see, just so that is also important, that we know the quadrants, the location of each sigma at that t number and n terms. And what can I say? There's really no like rule of thumb, or nothing to generalize for each loop. It changes forms. Sometimes it's linear, sometimes it's curved, or both. Sometimes the lower values curves, and then linear for the higher values. So many arrangements, so many shapes. But what is consistent is that, at higher t numbers, especially the second to the fourth list, sigma 0.5 is closest to the zero, because it is tuned in or aligned to 0.5. So it is the closest to zero, and all other sigma, because it's not really tuned or aligned, the t numbers isn't from their sigma. It could have many, different shapes that can form. You can have a hyperbola, curving, bending, linear, and in many different quadrants. There's so many shapes that can happen, and it's also because the cosine and the sine, are all circular, cyclical, to periodic. So the theta, the angle that we are passing, changes the shape, and so many things can, so it can be in many different shapes and locations. So that's what we are seeing. These are the locations of the other sigmas when plotted in a graph, in a Cartesian plane. So